All right, today we're going to talk about using the power rule to find the derivative and how we can apply that information to find equations of tangent lines and normal lines. Last lesson you should have watched a video and familiarized yourself with the process of the power rule. Right here I have a function, just a polynomial that I will take the derivative of using the power rule. Now, one thing you should know whenever finding the derivative with this function notation, a lot of times they will write a little dash on the top, which is read as a prime. Okay, so this is h. I'll read this as h prime. Okay, and we're going to use the power rule to take the derivative. Well, the power rule is relatively simple. You take your coefficient times your exponent and reduce your exponent by 1. Okay, now what this is a shortcut to a much larger, longer process for finding a derivative that involves limits and the distance between the two x values approaching 0. Okay, we talked about that last class where typically with the slope you need 2 points, but if you want the slope at 1 point, what we do is we create a situation where the distance between the points is basically 0. It's so small. So there is a process on using limits in the slope formula to basically find this expression. Okay, so what we're doing is a shortcut, and if you're curious on why this works, I can definitely help you with that. Just shoot me an email. So what we have here is this is the equation for all the slopes at the function. Okay, like for example, if I wanted to know the slope at x equals 2, I can use this equation, and I could just do h prime of 2. Okay, and I can plug 2 into the derivative equation that I just found, and I would get, using my calculator, negative 0.25. All right, so that makes sense. If you go over here to x equals 2, and it's always helpful to have the graph of the function that you're looking at to see if your calculations make sense. If I evaluated this and I got like a 4 here for some reason, that would not really match up to what's happening at this location. I can kind of imagine the tangent line doing something like this. We could see that it's definitely going to have a negative slope as it just touches this graph at 1 point. Okay, so that's how we find the slope. Take the derivative, plug in your given x value. Now, what a common problem that you will see is needing to find a tangent line or finding the normal line at that point. So what we're going to do then is just kind of continue that. I'm going to find the equation of this line. All right, so the tangent line, or sometimes they just say tangent. In order to do this, you need a slope, or really to make any line, you need a slope and a point. Okay, so the point is like some x1, y1. Okay, so in this case, our slope is just the derivative evaluated at our x value. So our slope, we already found that to be negative 0.25. Okay, the point is most of it's given to us. We're told that x is 2. Okay, we got that from the problem, and now we just need our y1. Well, the y1 is the original function evaluated at 2. Okay, so our original function here at 2 should be somewhere. It should be close to 1. That's what our y value is. If you just imagine, how high up that graph is getting. So h of 2, I can put that in my calculator. and we can, or I could just do this real quickly. Let's see here, we got 0.25 times 8 minus 2.5 times 4 plus 6.75 times 2 minus 4.5. We got our calculator for that, and I believe it's going to give us 1. Okay, so I think I just did that in a previous problem, so I know that that's equal to 1. So there's our point, there's our x1 and our y1, and then our slope. So we can use our point slope form. Okay, which I've solved for y, that way I can put it in my calculator if I need to. Now I just fill in the blanks. So my tangent line is negative 0.25 times x minus 2 plus 1. All right, there's our tangent line. Now the another common question is maybe they want the normal line. Normal again is just perpendicular. Okay, so we've done this before. If you're given a parallel slope, or if you want to find the perpendicular line, you just do the opposite reciprocal. So the slope of your perpendicular line will be the opposite, so reciprocal of that. So instead of negative, it'll be positive. So it'll be 1 divided by 0.25, so which is 1/4. So this is just going to give us a 4. So our perpendicular slope, I'll use that perpendicular symbol here to the best of my ability. Alright, so our normal line is, again, it'll be very easy. You just have to change the slope. Okay, we can use the same point because that's not changing at all. Okay, plus 1. So what that's going to do is it's going to create a perpendicular line right here. Okay, so we can see that slope is going to be positive and something a little bit greater than 1. All right, so let me look to see if we did this right. I'm using GeoGebra to create my graph. So I'm going to go ahead and show our objects, and yeah, we can see that our point was 2, 1, okay, using the function, and our equation line is negative 0.25x plus 1.5. We could get that from, if you want to change it to that form, it's just a little bit of algebra. To do that. Okay, so a little bit sloppy here, but you can see how we're just distributing and combining like terms. Now, I'm fine with either answer, so don't feel like you need to expand it out for any reason. All right, so that's the perpendicular and tangent line if given an x value. Okay, another type of problem that they will ask you to find is, if you're given a slope and they want to find where that slope occurs. So the problem I just worked, we found the slope at x equals 2, and we used our function, our derivative, to do that. And so what I've done here is just so we can see what it looks like. I've graphed the plotted the graph of the derivative. Okay, so there's a few things I want to point out. First of all, the graph of the derivative is a representation of all the slopes along the graph. Okay, so the y values for this orange line are actually the slope of the blue line. So for example, we did x equals 2, okay, and we saw from the last video, or the last segment, that our derivative was negative 0.25, and we can see that here in this orange line is somewhere between 0 and 1, about a fourth of the way. So that's negative 0.25. All right. There's a couple other things that are important when dealing with the derivative. Okay, one of the most important things is if you notice the maximum and the minimum of our original graph, these local extrema, what they're called, is they correspond to the x-intercepts of the derivative. Okay, and that's because the slope here in this function, the slope at these max and mins, these are horizontal lines if you imagine the tangent lines. So the slope is equal to 0. Okay, that's some information that you'll need in the next couple in the section towards the end of this chapter. Okay, so if you wanted to figure out find the max and mins, you just need to figure out where the slope of the function is 0, and so that just involves you're solving h prime of x equals 0. Okay, but we're not doing that right now. Right now we're looking at some other problem I'm going to make up here. So we just found in the last segment the equation of the tangent line at x equals 2. Okay, so it was here. I think we figured out that it was negative 0.25x plus 1.5. Okay, so we got that from our equation. So my question to you then is, where else is the slope equal to negative 0.25? Okay, so that's what we want to find out. All right, somewhere along this line, the slope is again negative 0.25, which would make the tangent line at that x value that we're looking for. It will make it tangent to the one that we've already found. Okay, they'll have the same slope. Okay, and so it's asking where. Anytime you see the word where, that means you want to find an x value. Okay, so we've already got one. We already figured out that one place where it's equal to negative 0.25. Okay, and that happened at 2. All right, we want to, so again, that's the slope. So here's is a negative 0.25 somewhere. Looks like it's like right about here. It's broken up into 5 segments. Okay, so imagine somewhere here before it gets to be 0, it's going to have a slope that's also negative 0.25. Okay, so that's one way to kind of look at it, just seeing how the graph behaves. The other way to look at it is, like I said before, this derivative, the y values of this derivative are the slope of the blue line. Okay, so we found that x equals 2. This has a value of negative 0.25. All right, so where else does that happen on this graph of the derivative? Well, that happens over here. Okay, so whatever this x value is the location that we're looking for. Okay, so all we have to do then is just solve h prime of x equals 0.25. All right, and I'm going to do that with our TI Nspire. I'll show you how to do all of this, but basically all we need to do is find the intersection. Okay, so find the intersection of h prime of x and the line y equals negative 0.25. So I'm going to graph on my TI Nspire. I'm going to show you how to graph the derivative, and then we'll do a process we've done before where we just need to find the intersection. Okay, so I'll do that right now. So here we are in our TI Nspire, and we're going to continue that last problem that we worked on. What I'll need to do is create a graph so we can see something similar to what we were looking at. I'll show you a couple different ways to do this. The first way is going to involve me typing in the original function. So it's 0.25x cubed minus 2.5 x squared plus 6.75 x and then minus 4.5. Okay, I'll hit enter, and something similar to what we've been dealing with shows up on our screen. Okay, good. So with this function, it's relatively easy to put in the derivative since we've already figured out what it is. So this is the first method. You just, on a separate line, just graph the derivative. Okay, so we had 0.75 x squared minus 5x plus 6.75. Okay, good. It's on there. Nothing too difficult about that. Okay, but because this is a scientific or graphing calculator, there are a lot of different tricks that we can use. So I'm going to show you how the calculator can also do this. I'm going to turn this off, click this off, and I'm going to enter in the other method on the next line here. Okay, so I've got my original function graphed into F1. So what I'm going to do is I'm going to use the derivative function command operation in the calculator to generate my my derivative. So I'll select my little option, not that one, sorry. I want to select, there we go, and push this little button with the squares on it, and I'm going to go down to this little icon that says derivative. Okay, not that one. That's this. This is the second derivative, which we'll get to later. This is the first derivative. Okay, so I'm going to select that. I'll hit enter. Now I want to take the derivative with respect to x. Okay, that's all. That'll always be the case. You'll never enter in anything different there. And then here you're going to type in your function. So I have f1 of x. Okay, just referring to that first line. If you don't have anything entered into F1, this isn't going to work. So we'll hit enter, and it generates the graph we just saw. So I'll show you how they are in fact the same here. You should see them overlap when I turn this on. Okay, there you go. So boom, a couple different ways to graph the derivative. The second method is pretty helpful if, number one, you don't want to make any algebra mistakes when you do your derivative, power rule, whatever. Your calculator will generate it for you correctly, assuming you type your original function in correctly. All right, so let's just use that one we just put in there. All right, so now the question asked us to find where else is this this function equal to, where else does this function have a slope of negative 0.25? Well, in order to do that, I need to enter in a negative 0.25 into my calculator, and we can see this purple line shows us two intersections. This first intersection happens at x equals 2. Okay, we can see that approximation there. We want the other location where it's 0.25. Okay, so that'll happen at this other intersection point of the derivative. Again, the derivative, all these y values represent the slope of the blue line. Okay, so we can see where the slope here is 0 at the top. Here between the two, the max and the min, is going down, so the slopes are all negative down here. They're negative y values, and then it comes back up to be 0, and then now we're back to those positive y values for the positive slope. So we want to find where it equals 0.25. So I'll go to my menu, I'll do my analyze graph. I'm going to go to intersection. I want to find the intersection between the two graphs. So the first graph that I want is this horizontal line, and then also my derivative, okay? Because I want to know where the slope is equal to negative 0.25. So I'll do my upper bound and lower bound. Here we go. And we see that it happens at 4.67. Okay, good. And there's our answer. All right. So that is the location that this line will be, this tangent line will be parallel to the one that we found. This is the other location where it has a slope of 0.25. Okay, so that would be our answer. X equals 4.67. All right. With that information, that should be enough to get you through the lesson, to do any of the problems in the first set of questions and even the second set of questions. All right, if you have any questions, let me know.